Assalamualaikum everyone, welcome to the course of Real-Time Embedded Systems. So we were continuing our chapter interfacing in our previous lecture, and we talked about types of interrupts, we talked about fixed interrupt, we talked about interrupt vector, and then we talked about compromise between fixed and vector interrupt. That is our vector interrupt table. We talked about IOs, memory mapped IO, we talked about standard IOs. So in today's lecture we will start from our interrupt routine. So let's start this chapter. So as I've already told you at the end of previous lecture that interrupt driven IO using fixed interrupts. So in this diagram you can see that how the steps vary when we move from fixed interrupt to vector interrupt. So this is the time. So these are all the cycles that 1A, 1B, 2, 3, 4, 5A, 5B and 6. So what happens? In first cycle, microprocessor is executing its main program, so it is similar to what we were doing before. In 1B, port 1 receives input data in register with address this 0x8000. In 2, P1 assert interrupt to request servicing by the processor. So what happens in third cycle? After completing instruction at 100, microprocessor sees interrupt asserted save PC value of 100 and asserts int A. So now there is an addition that whenever the P1 asserts int, that is interrupt. So at third cycle, after seeing the interrupt, the microprocessor corresponds to the interrupt by asserting interrupt acknowledged. So this int A is interrupt acknowledged. In 4, P1 detects interrupt A, interrupt acknowledged, and puts interrupt address vector 16 on the data bus. So we are putting the interrupt address vector 16 on the data bus. So previously you know that our address was fixed for the ISR, but now we are putting the address on the data bus. Microprocessor jumps to the address on the data bus. So now the microprocessor will jump to the address on the bus, that is 16. The ISR reads data from this location, modifies the data and writes the resulting data to 8001. So this is similar to what we were doing before. In 5th B, after being read, P1 deasserts int. So now P1 will deassert its signal, that was interrupt signal. In 6th, the ISR returns. So the ISR will return to its main program. So we can restore PC to 100 plus 1, that is 101, where microprocessor resumed executing. So now we will look into the timing diagram or step-by-step process of how these things is being done. Let's move on to next slide. So in interrupt driven IO using vector interrupt, you can see we have a program. We have interrupt service routine at 16, 17, 18, 19. We have a main program. Then we have microprocessor, and then we have two signal. Interrupt that is coming from port to microprocessor, and then we have interrupt acknowledged that is coming from microprocessor going to port 1. And then we have these ports connected to system bus, and system bus is connected to data memory and microprocessor. So in 1A, microprocessor, it's not P, it's UP. Microprocessor is executing the main program. So in first cycle, the microprocessor is executing the main program. So what happens? P1 receives input data in this particular register. So P1 receives input data in 0 cross 8000. Now in next cycle, so this is the data that is received. Now P1 asserts int to request servicing by the microprocessor. So you can see here that int is 1. Okay, so int is 1 here. In next cycle, after completing the instruction at 100, so you can see program counter as 100, microprocessor sees int. So now it is saying int, and in return it will acknowledge the port. So we can see that interrupt acknowledges 1. Okay, so P1 detects int A and puts interrupt address vector 16 on the data bus. So you can see here, that after acknowledging, it puts data on the data bus. So in 5A, let me so in 5A, what happens? PC jumps to address on the bus. So what happens? Program counter loads itself with 16 because this address was on the data bus. So you can see here the data is moving from 6P1 going to microprocessor, and then program counter is loaded with 16. The ISR reads, so it is reading using the statement move R0 0x 8000. Then it modifies R0, move R0 into 8001. So you can see here, this is moving 8001. The data is coming into 8001 memory location of the port. After being read, P1 desert int. So once it is read, now you can see that int is 0. Okay. So this is the whole process of interrupt driven IO using vector interrupt. So one thing that you need to understand here, that the ISR is not at fixed location. We are providing the location from P1. Okay. Secondly, there are two signals, that is interrupt and interrupt acknowledge. Rest of the things are same. So finally in 6 the ISR returns, thus restoring the PC. So you can see that we are moving from this ISR to main program. PC is loaded with 100 plus 1 because we already executed this 100, and now the microprocessor will resume its process from 101 instruction. So it will start executing the 101 instruction. So the final interrupt type is interrupt address table. That is a compromise between fixed and vector interrupts. So here we have one interrupt pin, table in memory holding ISR addresses. So we will have a table that will hold the addresses of the interrupt service routine. It can be like 256 words. Peripheral does not provide ISR. As in the previous case, we have seen that 16 was stored in the register at particular memory location. So peripheral does not provide ISR, but rather index into table. Okay, so we will have a table which will contain the address of the ISR. Now fewer bits are sent by my peripherals. Can move ISR location without changing peripherals. So we can change the interrupt service routine location without actually changing the peripherals, and very less bits are sent by the peripherals. So let's move on to next slide. So in this slide we will talk about the additional interrupt issues. So what are the issues? So basically we have external interrupts which have two types, maskable versus non-maskable. So both of these are external interrupt. In maskable interrupt, programmer can set bit that causes process to ignore interrupt. So what happens? Programmer can set the bit that causes processor to ignore the interrupt. So whenever we are using the maskable interrupt, it means that we can set a bit so processor does not need to do something on the interrupt. It will simply ignore the interrupt. This is important when in the middle of time critical code. For example, if you are executing some very critical code, we do not want any peripherals to disturb the processor by issuing some interrupt. So what happens? We use maskable interrupt. In non-maskable, a separate interrupt pin that can be masked. So we used a separate interrupt pin that cannot be masked. So we cannot mask it. Typically serve for drastic situation. So Non-maskable is used for drastic situation like power failure. We need to generate some interrupt, immediate backup of data to non-volatile memory. So in maskable, we basically ignore the interrupt. In non-maskable, we have pin that cannot be masked. So we use non-maskable for the cases for emergency situations like power is failed. So we need to back up all the data to non-volatile memory. And another issue is jump to ISR. Jump to ISR, some microprocessor treat jump same as call of any subroutine. So jump function is just like some independent function or it's just a routine. So some microprocessor treat jump same as call of any subroutine. Complete state safe. So whenever we are treating, when microprocessor treats that it's a subroutine, we are saving the state. That is, we are saving the value of program counter, we are saving the value of register, which can take hundreds of cycles. Now, other only save partial state. So, in computers and microprocessor who do not treat interrupt service routine as a complete subroutine, they only save partial state like only PC. We are not going to save the value of all the registers. Thus, ISR may not modify registers. So that once you are just saving the value of program counter, what happens? Your interrupt service routine cannot modify the registers, or else must save them first, or otherwise we must save. So in previous case we were saving the registers so that we can modify them, but in this second case we are only saving PC, so we cannot modify register. If you have to do so, you must need to save them first. Assembly programmer must be aware of which register stored. So if you're assembly programmer, you must be aware, you must need to understand which register stored. Not every register can store. Okay, so let's move on to next slide. So after discussing the issues of interrupts, now we will talk about direct memory access, or also known as DMA. So there are three things that we need to understand, that is buffering. First of all, buffering is temporarily storing data in memory before processing. Data accumulated in peripherals commonly buffered. So what happens when we need to process some data? It must be stored temporarily, and for that purpose we use buffering. Now what happens? Data is accumulated or data is gathered in the peripherals known as buffered. Now microprocessor could handle this with interrupt service routine. So rather than buffering, what we can do, whenever the data is accumulated on the peripheral, we can issue an interrupt and microprocessor can handle it. However, storing and restoring state inefficient, as we have seen that in case of interrupt we have to save the program counter, we have to save the value of register, which is quite inefficient. And the main program which you are executing, you have to wait. So regular program must wait. So we usually avoid this and we take advantage of direct memory access. DMA controllers are more efficient. Why? Because DMA uses separate single purpose processor. Microprocessor relinquishes control of system bus to DMA. So we can release the control of system bus to DMA. So microprocessor will no longer be using the system bus. Rather, it will give the control of the system bus to DMA controller. Microprocessor can meanwhile execute its regular program. As in the case of interrupt, we have seen that microprocessor access the system bus, and then it goes to interrupt service routine while halting its main program. Here the microprocessor will only give the control of the data bus, and it will keep on executing its regular program. So what happens? No inefficient storing and restoring state due to ISR call. So we are not going to store program counter, register, and then we are not going to restore those registers and program counters. regular program need not to wait unless it requires a system bus. So your regular program does not require to wait unless or until it requires the system bus, which is now granted to DMA. In Harvard architecture, processor can fetch and execute instruction as long as they do not access data memory. So we know that in Harvard architecture we have separate program memory and we can have separate data memory. So in Harvard architecture, processor can fetch and execute instruction as long as they do not access data memory, because for accessing data memory we need data bus. So if that is the case, if processor needs to access the data memory in case of Harvard architecture, then we must need to wait. It is known as processor stalls. Let's move on to next slide. So in this slide we will check, like for example, peripheral to memory transfer. So we need to transfer some data from peripheral to memory without direct memory access. So we are going to use vector interrupt. So we know that in vector interrupt, microprocessor is executing its main program. There is some P1 receive input data in register with address this 0x8000. Then P1 asserts interrupt to request servicing by the processor. In third interrupt, after completing the instruction at 100, microprocessor sees this interrupt. So microprocessor sees this interrupt, asserted save PC value of 100 and asserts interrupt acknowledgement. In 4, P1 detects interrupt and puts interrupt address vector 16 on the data bus. So after detecting interrupt A, P1 puts data on the data bus. So microprocessor jump to that particular address on the bus, that is our 16 address. The interrupt service routine at 16 read the data from 0 cross 8000 and then write it to this particular memory location. So what we are doing, we are writing to memory location. We are not saving it into the port, rather we are writing it to the memory location, that is 0x001, which is a memory. Now in 5b, after being read, P1 deserts, so we deserts this signal P1. In 6, the ISR returned, thus restoring PC to 100 plus 1, which is 101, where microprocessor resume executing. So it requires, you can see, it would require 6 cycle almost in case of no DMA. So let's move on to next slide. So in this slide we will see how things moves up in step-by-step process without DMA access, how we can transfer from peripheral to memory. So microprocessor executing its main program. So this is the main program microprocessor executing, and P1 received this data. So there is some data, as you can see here. This is the data with address 0x01. Now in second, P1 asserts interrupt. So you can see int is 1 and it is requesting processor to service it. And next, the program counter is getting stored and it will see microprocessor see with interrupts, and after seeing interrupt it will assert a signal, that is interrupt A, to the port. In fourth, P1 detects int A and puts interrupt address vector 16 on the data bus. So you can see here, now after seeing int A, it is putting the interrupt address vector. So this interrupt address vector 16 is put on the data bus. So here you can see. Okay. Now at fifth, microprocessor jumps to interrupt service routine on the 16. So microprocessor will jump here. Now after going through these 3 instructions, it will read. Here it is reading, here it is modifying, and then finally it is moving. So there is some, we need to correct this. This is not 0 cross 8001, rather it is 0 cross 0001. So this is a mistake here, because at the end we need to, you can see here in 5a, this is what is happening, and 5 this is happening, and 5b the interrupt signal is getting deserted, and this is also happening. So we are putting the data back to the memory. Okay, so processor is putting the data back, so data is coming from here port going to processor, we are doing interrupt, and then it is going back to memory. So this is how we put data from peripherals to memory using vector interrupt. And finally in 6 we are going to increment the program counter. So you can see here the program counter is get incremented with PC plus 1, and it will come back to main program. Okay, so it will start executing from the instruction 101. So that was about the peripheral to memory transfer without direct memory access using vector interrupt. So in next slide we will see that how we can transfer from peripheral to memory with the help of direct memory access. So in that we will see how it is efficient. We do not need to save PC while the program counter will run its main program, while with the help of DMA we can do rest of the things. So let's check it out. So this is the flow of the peripheral to memory transfer with the help of DMA. So you can see that we have one additional cycle here. However, this is more fast and more efficient compared to vector interrupt, where we were not using direct memory access. So in one, microprocessor is executing its main program, and it has already configured DMA control register. So it has configured the DMA control register in one. In 1B, P1 receive input data in register with address 0 cross 8000. In 2, P1 assert request. So we do not have interrupt here, we have request. So P1 assert request to request servicing by DMA controller. So P1 is now requesting DMA to service its request. So in 3, you can see here DMA control asserts D request to request control of the bus. So in third, the DMA will request microprocessor to give control of the bus to DMA. So after executing instruction 100, microprocessor sees this request by DMA, sees D request asserted, release the system bus. So it will release the system bus, asserts D acknowledge. So it will assert the signal D acknowledge, meaning that it has seen D request and released the system bus and resume execution. So it after doing so, after releasing the system bus, it will resume the execution of its next instruction. Microprocessor only stalls. It will only stop working, or it will only go into the wait mode if it requires the system bus for executing. In 5, DMA control asserts acknowledge. So DMA control will assert acknowledge, read data from this location and writes data to this location. So now we are reading the data from 8000 and writing the data at 0001. Whereas in 6, DMA desert D request and acknowledge, completing handshake with P1. So once this is done, it will desert the signal of D request, that was sent to it by P1. In 7A, microprocessor desert D acknowledgement and resume the control of the bus. So once DMA is done request servicing the P1, the microprocessor will assert D acknowledgement and resume control of the bus. In 7B, P1 deassert request. So we are asserting and deasserting lots of control signal. Here number 1 is request REQ, number second is DREQ, number 3 is DACK, and number 5 is ACK. So let's move on to the step-by-step flow of this strategy in next slide. So here you can see that we have program memory. We do not have any ISR. So there is no ISR, the main program is here and processor will keep on working on this main program. We have microprocessor with program counter and two control signal, D acknowledgement and D request. We have data memory as in the case of vector control, we have it like exactly the way it is in this slide. We have data bus and we need to get control of this data bus. Okay, so we are going to request microprocessor only for this data bus. So this is our port. We can see here that the port is connected to DMA control, and in return DMA control is connected to microprocessor. So microprocessor is executing this main program and it has already configured. So this DMA control registers are already configured. P1 receives, so this P1 receives address. This P1 receives input data in register with address 0 cross 8000. So this is coming. So you can see here the data is coming. So data is here. So in next state, in next cycle, P1 assert request servicing by DMA. So we can see here, this is the request asserted by P1 to DMA. DMA control assert the request. So now DMA will request the processor. So here you can see DMA requesting the processor for this system bus. Now what is happening? You can see that the microprocessor is acknowledging the D request and it is sending the signal D acknowledge to DMA and giving this bus to the DMA controller, and it will start executing its instruction 101. So in 5, DMA control asserts acknowledgement. So you can see here DMA control asserts acknowledgement, reads data. So it is now going to read data from this 8000. So you can look here, data is being read. Okay, we perform some operations are performed, and then finally the data is written at 0 cross 0001. Meanwhile processor is still working. Okay, now in 6 the DMA deassert. So in 6 we are going to deassert the signal. So in this slide we will talk about the peripheral to memory transfer. So only last step was missing. So in 7, a microprocessor desert de-acknowledgement and resume control of the bus. So you can see here the DAC signal is now 0. So microprocessor now control this system bus, and peripheral P1 desert request 0. So now you can see that peripheral this P1 desert request signal. So there is a last step. There is 7A and 7B. So we have seen here that we do not require any ISR in program memory. Rather, we are placing the DMA controller in between peripheral and microprocessor, and the only purpose of, or the only goal of DMA is to get control of the system bus, and it gets control of the system bus as long the main program does not require system bus. So that was about the peripheral to memory transfer with DMA. Let's move on to next slide. So in this slide we are being told about the ISA bus DMA cycles. So the bus that is used here is industrial standard architecture, and it is using DMA. So we can see that processor is connected to DMA and the bus is connected to memory as well as IO devices. So this is request and this is A is acknowledgement. So IO is requesting the DMA, DMA is acknowledging, and then DMA is requesting processor and processor is acknowledging. So we are getting control of this bus through DMA. So these are DMA memory write cycle, and this is DMA memory read bus cycle. So we have 7 clock cycles, as we have seen that it requires 7 clock cycles. So these are cycles, this is clock signal. The only difference between reading and writing is that in reading you can see here that our memory read operation is performed first, then we are going to write, whereas here our read operation is fast performed first, then we are going to memory write. So these two operations are flipped. In reading we first read and then write. In writing we first read and then write. So rest of the things are same, that we are reading the data in 5 to 6 clock cycle. At 5th or 6th clock cycle we are reading the address throughout all the clock cycle. For this we are using address latch enable. So to keep address on the bus we are using latch. So this is memory read. So this is going to work because this is slash memory read. It means that it's going to work on logic 0. So during third and fourth, and yes, during third and fourth clock cycle we are going to read. So this is initiated, and in fifth clock cycle we are basically reading the data. So IO write. So once we are written, we are going to read the data, and channel ready is just telling you that we have channel ready. So this is the same, all the things are same except that we are first IO read, we are doing the operation of IO read, then we are doing the operation of IO memory write. So we are going to write in the memory in 5th or 6th. So this is just about using DMA with ISA bus. So thank you very much. I hope you understand this.